All right. Hello, everyone. My name is Austin Harris, and in this video, we're going to quickly go through, excuse me, walk through the problem 4 on the final exam. Well, it's problem 6 on the exam, but it's the fourth kind of regular problem. So, in this problem, we're asked to modify the least common subsequence problem or algorithm in order to identify what's known as the heaviest common subsequence. And we're going to use a weighted scoring scheme, which you can see in the matrix on the top left of the page. So, for example, with a B and a B match, the weight will be a 2. So if you're watching this, I'm sure you've already read the problem, so I'm going to hop right into it. So for part A, first illustrate the application of dynamic programming on a heaviest common subsequence using the example of X and Y sequences given above by following the example of figure 15.8 in the CLRS textbook. So first off, so in this problem, I kind of did what I did on the rest of the problems. I kind of wrote everything I wanted to say out. That way, if Dr. Chin didn't have time to watch the video, he would kind of at least see what I talked about. So in this problem, in order to show the application of dynamic programming, I will first show a table that's similar to the LCS algorithm shown in the book. And this table will allow us to calculate the heaviest common subsequence, very similar to the way the longest common subsequence is calculated. So I also want to just real quick, I don't want to take up too much time, but I want to just mention, for a problem to meet the criteria of dynamic programming, it should have two main characteristics. The first, which we've all heard in class, which was the overlapping subproblem and subproblems and optimal structure, substructure. So for this instance, we will solve a complex problem of HCS with dynamic programming by breaking it down into subproblems and store the results with subproblems to avoid having to compute the same result more than once. Heaviest common subsequence contains the overlapping subproblem characteristic because we must compute the value of each subsequence, which we will combine at the end to give us the final overall heaviest common subsequence. So I also want to mention that my table may look a little, as at first, the first time I read this problem, I was, I knew I kind of had my work cut out for me. So as I was solving this problem, the first time I solved it, it made more sense to me. I actually mapped out these actual weights of 0.5, 1, and 2 to values, to whole values 1, 2, and 3. If you look at the table on the right side of the page, I hope that's all right. So, well, basically, whenever we get, a weight, whenever we get a match for BB or AB or AA, we'll grab its value from the matrix, just for the visualization of this problem. We'll come to this table and we'll map it to the table value, and we'll put that value actually in the table shown on the next page. So on the left-hand side, I hope you can see that. So the way this works, kind of the sub-problems you could think of, we start in the top left. We have given vector x along the top, vector y along the left side, and we start off, and for example, we're given b. Well, bb, if we go back here to this table, on the actual value, bb is a 2, and we see that on the left-hand side in the matrix as well, right? And let's see, it won't let me highlight just the 2, but it's where B and B meets. So that maps to 3. So we're going to put a 3 in here. And the way this table works, that's the top left 3, by the way. So once we finish, so basically, the way we get this, when you have a match, you look at the diagonal. If you have a match along, you go along each row. So we go first along the B row and we check each value at the top. And if there's a match, so a B and a B would be a match for B, and a B and an A would be a match. BC and BD are no matches. So in this table, when you get a match, you look at that diagonal up to the left value and to the value that you get from the table. So here, our value from the table was 3, but the upper left diagonal is 0. So we don't add anything to it, so it's just 3. Now, if it's not a match, what you do in this algorithm is you do the same thing in LCS. What you're going to do is you're going to look at the one above you and the one to your left. You're going to take the greater one, and if they're the same, you take the one above you. So with that being said, when you finish, what you do is you start at the bottom right, the greatest value, 13 on this table, and we're going to move. We're going to follow its arrows, and every time the value changes, we circle that. And this is going to give us our heaviest common subsequence. For X, the heaviest common subsequence is actually BA, and for Y, it is BA, and like I said, they're given by the heaviest squares, and those matched with each other give us a weighted score of 7.5. So on the right side, B, I have the pseudocode. The pseudocode is very similar to what we saw before with LCS. I point out that matrix M is passed in, and given 2 values, it's going to return the weighted value of the matrix, or of the match, excuse me. So that's where you see on the that's pretty much the main change. Besides the if statement, the first if statement you see in the pseudocode. I don't know if you can see me highlighting this or not. I think you can. So here, this statement basically says if it's a match or if it's not. So if it is a match, we do what we talked about in the table, where we get the value from the matrix. So we pass in M and N. We get the value of their match, and we just add that into the square, like we talked about. So I mean, and really, those are the main. That's the main change to this. Those 2 things are the main changes in this algorithm. I wish I realized that earlier on, because I had a really hard time with this problem. But once I understood it, it made it much easier for me to solve. I believe that is it for this problem. Thanks for watching.